Welcome to this exciting 4th edition of 15.18.2.13 and 15.5.13, where today, and only today, we get to talk about floating point numbers. Yeah! I'm excited. All right. The background, okay? Look, fractions are a pain in the ass. You learned that in like 4th grade, right? I mean, they are just a pain. They're still a pain. They always were a pain. At the end of the day, our numbering system that we like to think of things in is decimal, right? And the problem with a decimal-based numbering system is it can't represent everything perfectly cleanly, right? Like 1/3. 0.33333 repeating, right? What a pain in the ass. Okay? A binary number system is going to be the same way. There are some fractions that are just not perfectly representable in powers of 2. Furthermore, when we were imagining this set of real numbers, we had infinite precision, right? If I give you any pair of real numbers, you can put a number between them. Infinite precision, right? The numbers go all the way left, they go all the way right, and there's no distance between them. But that doesn't work in a world of finite memory. So not only do we have this problem that we can't represent things that aren't powers of 2 perfectly, but we also can't represent things to some arbitrary level of precision. All right? And so there are 2 ways we can basically deal with this. One is what is called fixed point numbers, and another is what are called floating point numbers. Okay? Fixed point numbers are essentially a different way of thinking about integers. Okay? I remember when I was a little kid, my grandfather ran a business. And he used one of these old school adding machines. And he would sit there and he would add up the different stuff he was selling. He sold coins. And he would add up the coins in this adding machine, right? The value, like this is a $20 coin, this is a $25 coin, this is a $32 coin, this was $18 coin, this is a 52-cent coin, blah, 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 blah. And just pound it all in on this adding machine, and then it would have the total on this little ribbon, right? And when he was typing in these numbers, like $22 and $35 and $45 and $45.27, he would never hit the decimal point. It was 4200, 3700, 6327. Why is it that he would never hit the decimal point? I mean, it's $63.27, $63.27, out of 100 cents, 63.27. Why did he never hit the decimal point? Ever. The whole time I watched him as a little kid, he never used the decimal point.
Valuing everything in cents?
In some sense, he was just valuing everything in cents, right? What's another way of thinking of that?
It's a fixed point.
It's a fixed point. He knew the right 2 digits were going to be pennies. Why would he waste his time hitting the decimal point? Okay? That's the fixed point system. We have 2 digits past the decimal. We have the integer component here, and then we have the next n digits, some fixed number of digits, of the fractional component. That's it. Okay? If you're thinking about numbers in terms of powers of 2, you just think of it in terms of scientific notation. Okay? If I have a fixed point system and I want 3 places worth of decimal, right? You can imagine that whatever number I have is actually multiplied by 10 to the negative third. Right? I just don't write the 10 to the negative third part because I know it. It's fixed point. The problem with fixed point is it's not very flexible. You fix the point. Right? It worked great for my grandfather because he didn't deal with half cents. Right? Nothing he sold was worth, $63.27 and, a half cents. $63, 27 and 1/8 of a cent. Didn't work that way, right? He always had 2 digits after the decimal. But sometimes that's not the way it works. You might work with some very small values and then some very large values. And since you have a fixed amount of memory, you have a decision to make. How much of that memory do I want to use to represent the range, the bigness of the value? And how much of that memory do I want to use to represent the precision? Am I looking through a telescope or a microscope? If I'm looking for a microscope, I don't want to have a fixed point system with a lot of digits to the left of the decimal place. There's nothing that big. It's all a fraction. If I'm looking through a telescope at a planet, right, I can't measure accurately enough to care about fractions. I need to measure big things. I need all of my decimal place, all of my storage to the left of that decimal place, right? And then for things in between, you might want to move that. So that's the freedom we have with a floating point system. Does that make sense? It lets that point float so we can capture larger numbers and smaller numbers with more accuracy. But it has some natural challenges, right? Because if I'm doing math, and I'm letting my decimal place, or in this case my binary place, float around. The problem is that if I have a really big number, it doesn't have the capacity to have a lot of precision when it comes to the fractions, right? And if I have a fractional number, it doesn't have the capacity to store something big. So when I multiply those two, there's a natural tension, right? Am I going to lose the ability to have the magnitude, the integer width, or am I going to lose the ability to have the precision in the fraction? How is that point going to float? And so, in a lot of math, where we understand what the range is, and the range is fairly stable, we use fixed point arithmetic. Okay? We don't use floating point numbers. We simply use integers. And as part of our code, we understand where that point actually is. But in a lot of math, we don't, either because we haven't done the analysis or the problem is dynamic, we need that decimal point to float, or that binary point to float. And so we rely upon floating point numbers. So like integers, floating point numbers are going to be different than real numbers, in that they're not boundless. They have a minimum value and they have a maximum value. Unlike integers, there's going to be what we call rounding, right? Really a type of approximation, okay, that's going to happen. Because with numbers closer to 0, our number line is going to be more dense. There are simply more points on our number line. With numbers farther from 0, they're going to be farther apart to get us that magnitude. Okay? At the end of the day, we're dealing with binary. Everything we're dealing with is coded as 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, whatever. There are discrete points on our number line. We can't change that. If we have a 16-bit number, we have a certain number of points in that number line. If we have a 32-bit number, we have another number of points in that number line, right? If we have a 64-bit number, right? Yet a greater number of points on the number line. But that's it. Given some width of number, we have a certain number of points in our number line. We can change the way we label them, we can change how we interpret them, but we can't give ourselves more. Okay? We can take this bunch closer to, this bunch over here and label them in smaller steps. And this bunch over here and label them in bigger steps. But we can't change the total number of points. Okay? So, the IEEE is an engineering organization, right? How many computer or electrical engineers do we have in here? Raise your hands. Right, so you guys know this organization, right? What is it? Yell it out. What does IEEE stand for? Oh, come on. Don't look it up. Who's a double E in here? You've heard of this. Yeah, forget the prepositions, like the Institute of Electrical and Electronics Engineers, right? I don't know if it's of or for, I forget. Right? Okay. It's the professional organization for electrical and electronics engineers, right? Computer engineers, right? And so, as an engineering organization, they care a lot about understanding tolerances, right? They care a lot about understanding how error creeps into things. Because one thing you learn as an engineer is there's no such thing as perfect, right? Did you guys learn that in like your first engineering class? I remember that from mine, right? There's no such thing as perfect. Everything is something plus or minus some tolerance. And when you build something, you have to worry about how those tolerances stack. Because that error can slowly add up, right? And so they were concerned about that in the numbering system. They were concerned how rounding What happens if we have an actual value that falls between 2 points in our number line? It's going to go here, it's going to go here. There's no point here. They were concerned about how that rounding stacked up and creeped in and affected computation. They were concerned there'd be a numbering system, right, that could be well understood, such that engineers using computer systems to do math could understand what the results meant. And so they developed a standard for floating point numbers. Okay. And so there's a couple of classic examples of numbering systems that had, in some way, shape, or form problems. The bottom line is, if you go and do reading on the web, you're going to find a lot of examples, in space programs and in military applications, where numerical problems cause things to blow up. Okay, in one way, shape, or form, cause systems to fail. Why do you tend to find it in these applications? Well, these applications tend to push the limits. Right? If you're dealing with commercial aviation, we try to keep things nice and safe, although there have occasionally been problems. We have a much wider margin of safety than if we're exploring, outer space with an unmanned probe. In that case, we just want to get as far as we can and collect all the data we can. And if it blows up, there's nobody aboard. We'll build a new one. Right? Military applications, sometimes you have to take more risk because there's risk in getting shot at. Right? And so you're willing to have a system that might fail a little more often if it gets you shot at a little less often. You've got to balance the risks when you're in a hazardous environment. But the bottom line is, in NASA with the Ariane 5, the Patriot missile system, there were situations where numerical problems prevented the system from working, and then things blew up. In one case, it cost $500 million. In another case, 28 people died. These things matter. If I look at this number, it shouldn't shock and amaze you that it's a binary number. Everything is in ones and zeros. We get that little subscript 2. Okay. No shock and amazement. This over here is what we call the binary point, like the decimal point, but it's a binary number, binary point. Going from the binary point to the left, we have 2 to the 0, 2 to the 1, 2 squared, 2 to the cubed, right? 1, 2, 4, 8, 16. Going to the right of the binary point, we have 1/2, 1/4, 1/8, 1/16, right? 2 to the negative powers. So our sum is just the same as it was before, except instead of starting at zero, we start at some negative number. And we add up the value across our positions. Okay? So if we start here, right, that's 1/2, that's 1/4, that's 1/8. We have 1 1/8, 0 1/4, 1 1/2, 1 1, 1 2, no 4s, and 1/8. The value of this in decimals is 11 5/8. Okay. Okay. So, divide by shifting right still works. Okay. We have the 2 to the 0, and to the right we have 1 over 2, 2 to the negative 1. So dividing by 2 still works to, right shift still works as divide, left shift still works as a multiply in this particular simple example. If I have something that's all ones repeating, that's a fraction below 1, right? How small? Well, if I would add point in this example, 0.000001, then that would become 1, right? If this is 1 repeating forever, we say it's an epsilon away from 1. Of course, it can't repeat forever because, why? Yeah, we have a finite amount of memory. So when we talk about epsilon, in this type of context, we're generally talking about some known small value. Some small value that either we've defined as meaningful in our application or is mathematically defined based upon the data sizes we actually have. Just like with decimal numbers, right? In decimal numbers, we can only represent things that can be represented as sums of powers of 10. Binary numbers, we can only represent things that are sums of powers of 2. Right? We had a problem if we were dealing with like 1/3. That can't be represented as a sum of a power of 10. So it's 0.3 repeating. Okay? We have the same problem with 1/3 as it turns out in binary. You can look at this and you can see it's 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. The 0, 1 repeats forever. 1/5. You can see the 0, 1, 0, 0, 1, 1 repeats forever. 1/10, right? Still, we see a 0, 0, 1, 1 repeats forever. Okay?
Was that a typo?
What are you looking at?
On the past pages, there were 3 zeros after for 1/10. Then there's 3 zeros, and then the
So my suggestion to you, I'm not going to work that right now to find out. Put it into a computer. Take a look. Print it out in hexadecimal. Then you'll know. 0x%x.
This is just right shifted by 1/5.
What's that?
1/5 to 1/10 is just
1/5 to 1/10 is right shifted by a bit. That's correct.
correct.
Look, I'm standing 2 feet from the slide. The ones and zeros all bleed together. So if the example is off by a 0, enjoy. I didn't expect you guys to do all the examples. The point was that for some fractions you have bits repeating, and that it can be a pattern of bits that repeat, not just a single bit. Okay. IEEE 754 is the floating point standard. It was established in 1985 for all the reasons we talked about, because engineers need to understand what the tolerances are. They need to understand how much error can creep in. At this point, the standard is supported by all major CPUs. Why? Because people who are doing scientific computation, right, need to have a standard they understand. If every processor implements a slightly different standard, it's going to be really hard for somebody who's a programmer trying to get something right. Because there's a lot of detail that comes into these situations, right? It's a nice standard in the sense that it has support for rounding, underflow, and overflow. It's not a nice standard in the sense that its floating point units are very complex. It takes a lot of transistors to get those things built and get them right. Floating point representation is essentially a form of scientific notation. Okay? If you think about scientific notation, remember that from like 4th grade or something? 2.5 times 10 to the third? Why do they call scientific notation scientific notation? Why did you use it like in chemistry and physics and, yeah?
Because in science you have both very big numbers and very small numbers, so it was an effective way to represent both.
Okay, so one reason is, right, in science you have very big numbers and very small numbers, and there's an effective way to represent both. It's a lot more fun to have, 2.5 times 10 to the negative 13th than have to write out a huge number of zeros. What else is really nice about scientific notation? Think about freshman chemistry class as a high school student. Yeah?
It helps with precision. You understand how precise, how many significant figures you have.
Significant figures, right? Sig figs. Remember sig figs? They're back. It's revenge of the sig figs today. Okay? This idea that when you measure things, the number you have, right, has a certain number of digits that you trust. Right? And in most of the sciences, you have a certain number of digits you trust, and then one you approximate, right? You say, I can exactly measure, I can exactly observe this thermometer is past the 2, and it looks like it's about halfway to 3. So I'm going to call it 2.5. I trust the 2. I'm estimating the half past that, the 5, right? And so you have one estimated digit or something, right? And then what was the detailed chemistry, right? Chemists were a little weird. Right? If you took chemistry class, they really took the sig fig thing seriously, didn't they? They had a special way of rounding. Anybody remember how they rounded? What did you do if you had something that you had, you'd done some computation and you had 3 digits, and the computation had 3 digits and you're only allowed 2 significant figures? You had to get rid of a digit. What did you do? Did you always round up? Did you always round down? What did you do? Yeah.
So if I recall correctly, you would round up or down, but if it was a 0.5, then if it was an odd number, you rounded down, and even if you rounded up, it was vice versa.
Yeah, you have the basic idea. So look, if it's less than half, you round down because it's less than half. It's closer to smaller. If it's greater than half, you round up because it's more there than not, right? But if it's exactly half, it's not fair to always round up because you get a bias. You're taking something that's half and always making it bigger, when really it's just as close to the smaller number. 1.5 is every bit as close to 1 as it is to 2. Why do we round up to 2? That's good for the tax man, I guess. Right? So chemists, I think, if I remember correctly, chemists round even. That is to say, if I have 0.5, if I have 1.5, I round to 2. I round toward the even. So I round from 1.5 up to 2. But if I have 2.5, I round down to even. Instead of going up to 3, I go down to 2. The philosophy there is that I'm rounding up as often as I round down. So I'm not introducing a bias. Does that make sense? So in a lot of ways, what we're doing here, you're going to see, is going to follow exactly that model. Okay? This is going to be base 2 instead of base 10. All right? But basically what I'm going to have is I'm going to have some fraction, okay, times 2 to some exponent, and then it's going to be negative or positive, just like sig figs. Right? Just like scientific notation with significant figures, right? You know, we might have in decimal, we might have 3.5 times 10 to the third, or negative 3.5 times 10 to the third. Now in this notation, right, we're going to have 1.101111 times 10 to the something, or times 2 to the something, I'm sorry. Okay? Now, what we're going to actually find is it's sort of interesting, right? What do we do with leading zeros? If I have the number 0010, do I care about the leading zeros? What do I do with leading zeros when I'm trying to put something in scientific notation? Throw them away, right? I shift until they're not there. If I have 00, if I have 0010, that's a 10, right? Well, if you think about binary numbers, this means that everything we represent in scientific notation, in binary, except for 0, is going to begin with what? 1. So actually, we don't need to store the 1 because we know it's there. Does that make sense? Either I'm storing 0 or it begins with a 1. Okay. So in representing one of these numbers, I have a fractional component. That's just like the fractional component for scientific notations in chemistry class, like 2.5. Except for the fact we're thinking of it in binary, and we know it begins with a 1. So we're just going to ignore that 1. Then we multiply it, like before in scientific notation, 2.5 times 10 to the third. Now we multiply it by some exponent. Except now, instead of 10 to the something, it's 2 to the something. Positive or negative. Okay? If it's positive, right, that's going to make the number bigger. If it's negative, that's going to make the number a fraction. So I have some fraction times 2 to an exponent, and that whole thing is going to be negative or positive as indicated by the sign bit. Sign bit's on, it's negative. If it's not, it's not negative. Does that make sense so far? Now, we have one small trick. I need to be able to represent a negative exponent, right? If I can't represent a negative exponent, what can't I represent? Fractions. Yes, I heard you say that. Fractions, exactly right. Okay? So somehow, this exponent needs to be able to represent, these exponent bits need to be able to represent positive and negative exponents. So remember I said, the number of bits in a binary number tells us how many points we have on a number line. The only decision we get to make is how we label them. The natural way of labeling these things is from 0 to some positive number, right? But we don't want that, because we want to have negative numbers. So we want to shift our labeling so that 0 is in the middle, and we have some positive numbers and some negative numbers. Okay? So I want to have about as many positive numbers as negative numbers, right? That seems fair. That's like the way we used to think. We like symmetry, right? So if I think about, let's say, a 3-bit number, what is the range of values of that number, just normally? From 0 to what? 7. Okay, so if I do nothing, I have 0 to 7. But ideally, I don't want 0 to 7. Okay? If I subtract 3, I have negative 3 to what? 4. If I subtract 4, I have negative 4 to 3. Does that make sense? That's what we call the bias. The amount we're going to subtract to shift our number line such that 0 is approximately center. Okay? Now the question is, what should that bias be? Okay? I'll come back to this in a minute. Okay? We have more math. This slide attempts to convince you that you need to do some weird stuff with math to figure out what the bias should be. Here's the thing. You don't. We know we want the range to be approximately even, right? We want about as many negative numbers as positive numbers. We know it's not going to be perfectly even because 0 comes out of which side of the number line? The non-negative side, the otherwise positive side, right? So, okay. If we look at a number, okay, this is a little weird. So if we look at a k-bit number, that is to say, a 4-bit number, a 5-bit number, a 6-bit number. Let's go back to my 3-bit number, a number that's 0, 0, 0 through 1, 1, 1. This thing suggests that the bias should be 2 to the k minus 1. Let's look at that for a moment. 2 to the 3 minus 1 is 2 squared, which is 4. Okay? So I have a 3-bit number, right, which represents 0 to 7. This says, if I look at the 2 to the k, the bias, that part, that's going to be 4, or about halfway, right? Would you agree? Halfway in that range is going to be 3 or 4. We all agree? So 2 to the k by itself, right? 2 to the k minus 1 is going to be 4. If I give you a 4-bit number, what's the range of a 4-bit number? 1, 2, 4, 8. The high order bit is 8. What's my biggest number? 15. It's 0 to 15. Okay? So what's going to be about halfway?
7 or 8.
7 or 8, right? Well, if I take 2 to the k, 2 to the 4 minus 1, that's 2 to the 3, that's 8, right? We agree? Why? Bit 0, bit 1, bit 2, bit 3. That's the value of my high order bit, which equals all my low order bits plus 1. Does that make sense? So my bias, as we've decided to do this, my choice between having my bias be slightly higher and slightly lower, what choice are we making here? If the bias is 2 to the k minus 1 power minus 1, what have we chosen to do with the bias? Make it slightly more than half or slightly less than half? Slightly less than half, right? So that's what we know. Given any number, all this says is the bias is going to be slightly less than half. Can't be exactly half. We're going to go in favor of slightly less than half. So if I tell you I have a 32-bit number, what's the bias going to be? Well, 2 to the 31 minus 1. But don't get wrapped up in that. Instead think, what's the biggest value this number can have? What's a little less than half of that? And that'll make sense, because you're shifting the number line by halfway. Okay? Since our bias is a little less than half, we're going to have slightly fewer negative numbers than positive numbers. Does that make sense? So you can see that here. For from negative 126 to 127, or negative 1022 to 1023. Do you see that? So that's how we're going to represent our exponent. When we think about our exponent, okay, if we need an exponent of 4, we're not actually going to store 4 in this exponent field. We're going to adjust it by the bias. That way we have the ability to represent a negative number. Okay. There are a few different IEEE standards: single precision, double precision, and extended precision. These are how the bits break out. Okay. Single precision is 23 bits for the fraction, 8 bits for the exponent, 1 bit for the sign. Double precision, 52 bits for the fraction, 11 bits for the exponent, 1 bit for the sign. Extended precision, 64 bits for the fraction, 15 bits for the exponent, 1 bit for the sign. Okay. So we've said we want things to work a little differently. I'm going to skip ahead a little bit here again. I'm never good playing with the rules. There we go. We've said we want things to work a little differently, right? We want a lot of points very close to 0. We want the points to be very close together. As we get farther away from 0, we want the points to be more distant, so we can get to bigger numbers. Greater precision for small numbers, less precision for big numbers. Okay? So the way we get more points like this, right, is not that we get more points, we have the same number of points, we just label them closer together. So you can see that there's a pretty big dividing line there. Okay? There's what we call normalized and denormalized numbers. The denormalized numbers are very close to 0. The normalized numbers are farther away. The denormalized numbers give us things that are very close to each other. The normalized numbers give us things that are farther away. Okay? So let's take a look at normalized values. Normalized values are going to exist when the exponent bits are not all 0 and the exponent bits are not all 1. Those are going to be used for special things. Okay? And we'll talk about that in a minute. The exponent is going to be encoded as the actual exponent we compute, 2 to the whatever, minus the bias. Why minus the bias? Again, that lets us have the negative part of the range. So we write, if I compute an exponent of 4, and I have a bias of something, what I'm recording is 4 minus the bias in the actual bit field. Okay? We talked about why the bias is 2k minus 1, slightly less than half. Okay? Okay, we already talked about the fact that in a binary number, I'm going to be leading with a 1, right? Because I'm not going to shift my zeros away. So I'm not going to bother to store the leading 1. It's implied. If I'm thinking 1.1101 times 2 to the 4th, I'm going to store 0.011 times 2 to the 4th. And when I go to interpret it, I'm going to interpret it as 1.011 times 2 to the 4th. So we don't actually store that leading 1, we just assume it. Okay? So if I'm trying to encode 15213 binary point 0, I write this out in binary. Okay? I shift until I have a leading 1. I count the number of times I shifted, and that's my exponent, right? Now, my exponent is 13, but I'm not going to record a 13 into my exponent bits. I'm going to adjust it by my bias. Okay? My exponent is 13, my bias is 127. I'm going to store a 140. Okay? Why do I add a 140? Because I'm going to subtract a 140 when I interpret it. Why do I have to subtract things when I interpret it? To get my range to back up so part of it can become negative. Okay? So I start out with my number and I write it out in binary. I shift to get a leading 1 and keep track of the number of times I shifted. That's my power of 2 exponent. I take that and add it to my bias. I'm adding it to my bias now, so I subtract my bias later, which is what gives me the shift of my range. I store my exponent plus bias in the exponent field. Okay, 140 in binary is 10001100, boom. Okay, this is my fractional component. I ignore the leading one, it's 1 point whatever's here, and I write out the rest. If I run out of room, because I have more bits in my fractional component than I have here, what do? What's that?
Round.
Okay, well, for the moment, let's just say I throw the extras away, and then we're going to get to the rounding. Fair enough? Okay. Now, this is what's called normalized numbers. Remember that on my number line, the normalized numbers are the ones farther from 0, that are giving me the big steps that let me capture a large range. Okay? Denormalized numbers exist where the exponent is all 0. Okay? If the exponent is 0, okay, then I'm dealing with this denormalized range. In the denormalized range, my exponent, my e, is actually going to be 0 minus my bias. Okay. That's a little confusing. I think that's probably the most confusing thing in this deck. Okay. My exponent is held at 0. Okay, do you see that? The exponent bits are always 0. I'm close to 0. I'm dealing with a fraction. I'm not bigger than 1 here, right? We'll deal with the details in a minute. But I'm dealing with a fraction. All right? So if I do that, I make my exponent 0 minus the bias, because that makes my denormalized range meet my normalized range. And I'll show you that in a second. Okay? If I didn't do that, then the two ranges wouldn't meet. I'd have a gap in my number line. Okay? So now, I'm going to assume a leading 0 instead of a leading 1. I'm going to shift until I have a 0.1 something, okay? So now that's my fraction. And then I go from there. The thing about the denormalized range is that because my exponent is fixed, my numbers are spaced the same distance apart. Does that make sense? If I'm changing my exponent, making it bigger and bigger and bigger, the points on my number line are getting farther and farther away. If I hold my exponent constant, then the points on the number line are equally spaced. That's why this is called the denormalized range. It's not normalized. It's not stretched. Okay? If my exponent is all 1s, this is a special thing. You see, you remember in integer math, we had all this weirdness if we wrapped around and we overflowed or we underflowed? That doesn't work for engineers. If it gets so hot, right, that you can't compute it, it's not okay to say it's cold. Right? We can't point our thermometer at the at the sun and say it's absolute 0 Kelvin or something, right? It just doesn't work that way. We can't wrap around like that. So what happens with IEEE math is that if you overflow, there's a bit that says we've overflowed, and it keeps track of the sign. Positive overflow or negative overflow. Positive or negative infinity. Okay? There's also something called not a number. It's what you get if you divide by 0 or take the square root of negative 1 or something like that, where you just can't represent the answer. And again, it keeps track of the sign. And so there's a positive nan and a negative nan. The really bizarre thing, and this is bizarre, is that there's actually a positive and negative 0. It's unavoidable because 0 is the bit pattern all zeros, right? But the sign bit can be on or off. So really bizarrely, there's actually a positive and negative 0, where the non-negative 0 is the same as the integer 0. All bits are zeros. Okay? So our number line looks like this. The denormalized range, which is equally spaced. The normalized range, we have big spaces. Negative infinity, positive zero infinity, and then nan. You can't really say that like not a number is positive or negative. There's a nan on the negative side, and there's a nan on the positive side. But like, is the square root of -1 positive or negative? Like, that doesn't work, right? And so nan, you can call it negative nan and positive nan, but like a mathematician will get upset. Yes?
What was the reasoning behind like throwing away all the possible numbers that could go there in favor of just labeling that entire range?
What else are you going to do? How many bits are you going to dedicate to representing things that you can't know? If you're trying to compute the trajectory for a missile and you end up with a nan, where do you want that missile to land? Right? I mean, you'd better know that you don't know.
Yeah, but like, why do they dedicate, like, to the 23rd possible spaces for that instead of, like, just one?
Okay, so you're asking why is nan a range rather than a specific number? And the honest answer to that question, the honest answer I have for you to that question is I don't know. I think the answer is that once you started doing special things, it makes it A, very hard to implement in hardware, and B, sometimes it makes it hard to implement in hardware, I think is what it comes to. The rules become complex, and it becomes hard to get it right. And that's a bad day. That's the best answer I can suspect. So this becomes a lot easier with examples. Here is an 8-bit number. There is no such thing as an IEEE 8-bit standard, but we're going to follow an IEEE-like standard. We have 4 bits for the exponent, 3 bits for the fraction, 1 bit for the sign bit. This slide, I think, is worth a ton. Excuse me. This slide, I think, is worth a ton. Okay? So we see our sign bit, we see our exponent bits, we see our fraction bits. Okay? If you look at this, you see where we go from the largest denormalized number to the smallest normalized number. Okay? When does this happen? This happens when the 1, 1, 1 becomes 1, 0, 0, 0. Do you see that? You remember I told you that the bias is 0 minus the bias because it makes the number line continuous? This is what I was talking about. If that bias were anything other than what it is, the 2 normalized range wouldn't meet the denormalized range nicely like this, where you can see that as we go from 0, right, to all zeros and a 1, we add 1 5/12, right? Add 1 to that, we get 1 0, 2 5/12, right? Add 1 to that, we get 3 5/12, right? 4 5/12, 5 5/12, right? Add 1 to that, we get 6 5/12, 7 5/12. And then even as we transition to the normalized range, we do that by adding still 1 5/12. Okay? So it's a nice smooth transition there. So there are several interesting points, right? The closest point to 0 has the bit pattern all zeros and a 1. Right? The largest denormalized number has all 1s for the fractional component and nothing for the exponent, right? The smallest denormalized number has a 1 for the exponent and 0 for all the fractions. Okay? The closest to, to 1 below 1, right? We can see a bit pattern for that. I don't know that's particularly interesting. The largest normalized number, right? Again, we can look at this bit pattern and we can see it's all 1s here, right? All 1s here and a 0 here. Why? If that becomes a 1, it becomes infinity. Okay? Smooth transition is really an interesting observation. Okay. And we can zoom in here and see what we mean about the denormalized range having equal space things, right? And the normalized range getting spread out. Floating point 0 is the same as integer 0 as long as we're talking about the non-negative 0. So this means that we can almost use an unsigned integer comparison. We can almost compare an unsigned integer 0 to an integer 0. But we must consider the negative 0 versus the 0. Nans are problematic, of course. What do you do with something that's not a number? Otherwise, we're pretty okay. Now, let's talk about rounding. So first, we want to understand what is, if we had more precision than we have, what is the exact result? Or at least the result of more precision than we actually need. Okay. Then we need to make it fit. Okay. If we can't, right, we need to round it so it fits in the fractional component, right? That is to say, we need to lose fractional bits in order to make it work. We talked about rounding. Okay. We talked about rounding towards 0 and away from 0. Okay. So think about the case of $1.40, $1.60, $1.50, $2.50, negative 150. Okay. If I have $1.60 and I round towards 0, right, that's going to take the $1.60 down to $1, right? It's going to take negative $1.50 down to it's going to take negative 50 down to a negative $1, closer to 0. Note that this became bigger, more positive by 50 cents, right? And this became smaller by 60 cents. That's because the rule is round towards 0, right, in that case, which is rounding in opposite directions depending upon which way you are in the number line. Okay? The non-negative side of the number line, you're rounding down. The negative side of the number line, you're rounding up. Okay? If we always round down, always round toward negative infinity, right, then we're always rounding, always rounding to the negative side of the number line, right? Then we see $1.40 becomes $1, $1.60 becomes $1, $1.50 becomes $1, $2.50 becomes $2, and negative 150 now goes negative 2, because we're always going left, the negative side of the number line. If we round up, it's the opposite, right? $1.40 becomes 2, $1.60 becomes 2, $1.50 becomes 2, $2.50 becomes 3, right? And on the negative side of the number line, negative 150 becomes negative 1. Why? We're rounding in the direction of the greater value, positive infinity. The default rounding mode in IEEE is to the nearest even. And it's to the nearest even for the same reason, okay, that it was to the nearest even in your chemistry class, to avoid that bias. If we always round up, or we always round down, or we always round in some weird way, eventually the always is going to generate a bias. Yeah! That wasn't fun at all. You're supposed to jump. Why didn't you jump? You're supposed to jump when I wake you up. That's the deal. Ah! Ah! I'm not sure he's alive. Ah! Ah! I think everybody here is too sleepless already in the semester. All right. So, the default rounding mode in IEEE is going to be to round toward the even. Okay? So, if we look at this, and we're trying to round this number to 2 decimal points, it's clear that it should be rounded down. Everything after that is less than half. In this case, okay, it should be rounded up. It's half plus something, closer to the bigger number. In this case, it's exactly half. Uh-oh! It's not closer to the bigger number, any closer to the bigger number than it is the smaller number, or vice versa. So what do? We round toward the even. Given the choice between rounding down to 1.23 and rounding up to 1.24, what do? 2 4s even. We round up. Okay? Here, 1.24, uh-oh, exactly halfway. Given the choice between rounding down to 1.24 and up to 1.25, we round down to 1.24. In one case, we rounded up. In one case, we rounded down. That's how we broke the bias. In binary, it's sort of more fun, because a 1 represents exactly half. So a 1 followed by all zeros is half. That's the case we round even, right? A 1 followed by anything is more than half. We round up. All right? So if I take a look at this, 1, 0, binary point, 0, 0, 0, 1, 0, and I want to round to 2 digits. I cover this up and I ask, is it less than half, greater than half, or exactly half? Well, it's less than half because that's not a 1. Round down. No question asked. Okay? Here, 10.00, cover up. Well, that's clearly more than half because it's half plus something. I round up. 10.01. In this case, I cover it. I end up with exactly half. Okay? Now the choice is between rounding down to 10.11, losing the half, or rounding up to 11.00. Okay? Well, the question is, what am I going to do? I'm going to round toward even. Is that even? No, it has a 1 in the ones place, right? So that's going to have to get rounded up to 11.00. That case confuses people a little bit, right? People, for some reason, want to get into this case and think that it's somehow between 10.11 and 10.10. 0.10 is going the wrong direction, right? Okay, here we have 10.10, 1000. So when I cover this, I'm in that half case again. My choice is now between rounding down to 10.10 or up to 10.11. 0.11 has a 1 in the rightmost place, so it's odd. So I round down to 10.10. Yes?
So rounding the 2 and 7/8 case is like rounding 19.5, isn't it?
Oranges are like apples, aren't they?
I mean, you're carrying it the same way.
I guess. Help me out. I'm not.
Like, consider the case 199.5. You're rounding it. You could round it by getting rid of the 5, which is what you were saying was wrong. Or you could round it and carry over until you get to 200 instead of 199 with some weird carry.
That's exactly right. So it's like if I have 99.995, right, or something, then I'm going to end up adding a little bit to round up.
Yeah, in the same way we do it over here.
In the same way we do it over here. Exactly. Okay. Floating point multiplication. What to say? If we're doing floating point multiplication, it's not really, in the abstract, anything complicated. We do exactly the same thing. We find the actual true result, okay, and then we get it represented as a floating point number. We shift until we have the right form. We find our bias. We record our exponent. We record as much of the fraction as we can, rounding even. Because that's what the IEEE standard requires. Okay? Okay. So, if we're too big, we shift to the right. Too small, we shift to the left. That changes our exponent. We overflow if it's out of range. We make our fraction fit, rounding as necessary. Okay. Floating point in C. Float is a single precision number according to the IEEE standard. Double is going to be a double precision number. If we're casting between a double or a float and an int, okay, it's obviously the case that if I go from a double or a float to an int, the int cannot handle the fractional bits, right? If my float is 1.5 and I'm trying to cast that to an int, it can't handle the half. It's an int. Okay? So it's going to truncate the fractional part. It's not going to round. IEEE standard about this rounding even only works within the IEEE floating point space. If I take a floating point number and I try to stick it into an integer, it's not going to fit, and what doesn't fit is going to fall out. Okay? So it's going to be truncation. What happens if you have not a number? Who knows? It'll probably turn out to be tmin. Okay? What if I try to cast an int into a double? That's okay, because as it turns out, a double is much wider than an int, right? Twice the width. So the full integer component of an int can fit into the integer component of a double. I will not lose anything. Okay? If I try to go from an int to a float, now I have a problem, because an int and a float are the same size. But the float loses the bit to the sign and loses a bunch of bits to the exponent. So the integer component is smaller. So I can't actually fit it into a float. Okay? And so when that happens, it's going to enter a floating point number, which is going to enter the IEEE rules. So it's going to round according to the rounding mode, round even. Okay? What to say? Floating point numbers are painful if you actually care about getting things exactly right. Right? I coached the programming team here for many years, and one of the classic ways that CMU blew problems that we otherwise should have gotten right was we would use floating point arithmetic, and we would ask, does x equal y? And we would do computation here and computation here, and they were equivalent, but because the math was done in different ways, the rounding happened differently. And so they weren't exactly equal. They were close. Because one of them started out with small numbers and blew up and got big and then got small again and rounded in one particular way that way. Another one of them started out with large numbers and multiplied them, rounded more, and then multiplied the small numbers and got smaller and lost more precision, right? And then if you do these in different orders, you may lose the same amount of precision, but lose it in different ways. Okay? Now your rounding all happens weird. So with floating point numbers, you really shouldn't use equal. You really should subtract the two and ask if they're less than epsilon, if the difference is less than some epsilon. Right? This is a natural thing to do for engineers because engineers are used to thinking in terms of tolerances. Right? Keep the washing machine door locked until the water level is less than x. Not until the water level is absolutely 0, because there may be a little bit left at the bottom, right? Unlock the stove after cleaning when the temperature is below blah, not when the temperature is exactly the same as the room. Because that's good enough to be safe, right? The two sensors, right, that are measuring airflow, right, should be within some epsilon of each other. They're not perfectly calibrated. But if they're more different than that, maybe the plane's wing is going to stall. Okay? So engineers naturally think in terms of tolerances. But computer scientists sometimes, we're used to discrete math. We don't think about tolerances, right? 1 is 1, 0 is 0, da-da, right? And so we have a hard time with this type of thing. And so, we think of math as as we learned it, and as we use it, and so we tend to forget about that. And so, it really actually, when you're doing floating point code, right, you shouldn't ask, does it actually equal 0? You should ask, is it close enough to 0 for my purpose? Okay. Other things that happen is you have to pay attention to how things round. After, I guess, toward the end of my undergraduate, and as I was beginning grad school, I did research in neural networks for a while. And I took this neural network I built this neural network according to a paper, and I demonstrated it to my bosses one week, and they're great. You have this great implementation of this neural network architecture. Now, try to solve this problem with it. Okay, here I did. Here's my results. Well, great. How long did it take you? 9 hours. Okay, that's not good enough. Go optimize that code so it can take less than a minute. Okay. And so I did a whole bunch of optimization, and then I came back like 3 weeks later, and I'm like, well, I've got good news and bad news for you. Okay. Well, what's the good news? I can do it in about 45 seconds. What's the bad news? It never actually converges. You know, and to which one of the bosses replied, well, if I wanted the wrong answer, I could do it much faster. Turned around to his keyboard and did printf hello world. And so we talked about this for a while. And we looked at the results and looked at some of the numbers and some of the cases and whatever. And one of my bosses said, well, it looks like there might be some type of numerical analysis problem there. Are you using floats for this? I'm like, yeah. He's like, I think you have some type of numerical analysis problem. And I didn't understand what he meant. And then I went back and looked at it and learned something about floats and realized that what I'd done, I'd gotten to the point where I drove values down to where they were really close to 0 and noise took over. The way I did the multiplication, right, generated noise that was then dominating the computation. And that's why beyond a certain point, I actually couldn't get a viable result. I couldn't get enough convergence for our purposes. And so I rewrote it using integers and fixed point. And so I've seen this crop up, a lot in a lot of different cases. So when you do the same computation different ways, you may end up in different situations. A plus B plus C may not equal, A plus B plus C. Okay, yeah. So here we have A plus B plus C, and we have B plus C plus D. And so here we have B plus C, and here we have B plus C. Right? The compiler may not be able to take that out and do the B plus C once. Okay, we look at this and say, okay, the compiler can do temporary equals B plus C, A plus temp, B plus D plus temp, right? Because to us, B plus C is B plus C. I can do that computation just once. But the problem is here, it's A plus B plus C, and here it's B plus C plus D. And it may actually round differently when I do the B plus C plus D than the A plus B plus C, right? So if I try to take that out, what could happen here is the A plus B plus C may not round the same as A plus quantity B plus C. Okay. We've got more puzzles, okay? And again, I don't think me doing the puzzles is helpful to you. I think you need to do the puzzles, okay? And then talk about them with your friends, right? And then come to office hours if you need help. But just take a quick look, all right? X is an integer, F is a floating point number, D is a double, okay? So I have some integer equals, I take X, which is an integer, I cast it as a float. When I do that, am I guaranteed to maintain the same level of precision? No. An int, X, and a float are the same size, right? But a float has bits that are dedicated to maintaining the fractions. So this is going to get rounded as X becomes a float. When I cast it back from a float to an int, that loses nothing. But I've already lost going from the int to the float. So at this point, my X here does not necessarily equal my original X. It rounded when X became a float. Make sense? Okay. Here, when I go from an int to a double, I'm okay. Because a double is twice as wide as an int, and it has enough integer bits to store a whole integer. So I lose nothing going from an integer to a double. And I certainly lose nothing taking those same bits back out and putting them into an integer. Since it started out as an integer, I didn't have any fractions to lose, so that'll be okay. Going from a float to a double, I'm fine, right? A double's twice as big as a float. Going from a double back to a float, I'm still fine. Okay. Going from a double to a float, obviously not okay. A double is twice as big, right? More precision. And so I'm going to let you sort of take them from there. one question is, like, if you think about this, I'll give you a hint as to how to think of it, and then I'm going to let you solve them from there. If I take f and I make it negative, and then I make it negative again, is that the same as f? The hint is it is the same if the number line is symmetric. The hint is it's not the same if the number line is not symmetric. Because then if I'm somewhere over here that's not representable over here, I could lose something. And then once I've lost it, I don't get it back going the other way. Okay? 2 divided by 3 versus 2 divided by 3.0. Again, I'm going to let you do that, but what I'm going to note is that this is integer division. And this is not, because that's a floating point number. Okay? Okay? And we see something there, so let you think about that. Here, if d is less than 0, does that imply that d times 2 is also less than 0? This is a question about rounding mode. With integers, it didn't, right? Because if I took a negative number and I multiplied it by something and I underflowed it, it became positive. The question is here, does that happen or does something else happen? Think about the special states that we have in IEEE numbers to prevent something that gets too hot from looking cold, or something that gets too cold from looking hot. If I have some double, I know it's greater than some floating point number. Does that imply that negative of that floating point number is greater than negative of that double? Okay. Well, what you want to notice there is this is d greater than f, right? So this is d, my double, to the right of my floating point number. Okay. D, magnitude greater than f. And on this side of the number line, it's negative f greater than negative d. Okay? So in this case, that sign is backwards, right? Negative 1 is greater than negative 2. Okay, so that's what you want to pay attention to in understanding that. And now the question is d times d greater than 0? Well, normally we'd think about a positive d and say, okay, if I have a 4, 4 times 4 is greater than 0, right? And I'd say the same is also true with negative numbers, right? Negative 4 times negative 4, the negatives are going to cancel out. But now the question is that going to work out in the case of floating point numbers? In the case of integers, not necessarily, right? Because I could overflow, become negative. Think about how IEEE handles that case. Okay. Does d plus f minus d equal f? Well, again, to most people, sure, right? We have associativity, commutativity. D plus f minus d is the same as d minus d plus f is equal to f. But remember the case of rounding. And although the commutative and associative properties are approximately true in floating point numbers, they're not necessarily exactly true. So think about what that means in this case. Summary. IEEE floating point standard has clear mathematical properties. It represents numbers in the form of scientific notation, specifically base 2 scientific notation. It's great because one can reason about the operations independent of the implementation. If I know that a processor implements the IEEE standard, I don't have to worry about which algorithms it uses to do math. Okay? It's not the same as the arithmetic you learned in math class. That approximation means that associativity and distributivity and commutativity don't necessarily work the same way, which makes life difficult for compilers. Why does it make life difficult for compilers? You and I might look at something and say, oh, I can remove this common sub-expression. The results will be close enough to the original for my purposes. But the compiler doesn't know your purposes, so it can't do that. So when it comes to floating point math, compilers can't do some of the forms of mathematical optimization they would do with integer operations, even though it might be fine with us, because they can't break things that were correct before they started. Okay? One more thing I actually want to talk about. Are you guys familiar with the Intel FDiv bug? Anybody heard of it? On the Pentium bug? So it's just a classic story about floating points. So floating point math in a processor happens in ways very, very different than you might think it would. Okay? Long division takes a lot of iterations. Okay? It's not a really good way of making things consistent in a processor. Okay? It's not a good way of making things go fast in a processor. So they use, if you learned about Taylor and Maclaurin series, like in some calculus class, right? They use series, basically, to understand what the results will be, and have tables of partial fractions, you know. And when they were, and these things were worked out years ago, okay? And so when they were building the Pentium processor, Intel's new flagship processor at the time, there was an intern who was given the job of loading this table onto the tape, basically, of loading this into the new processor design. And his Perl script had a bug and was off by 1. And it went unnoticed through their validation. And so every Pentium processor on Earth was built with certain, you know, with the ability to have incorrect results for certain divisions. And as I remember it, and I'm foggy here, I think it was a professor at Georgia Tech who was maybe a physicist or some scientist that had been doing these really precise experiments. And the graduate students were running them on this new equipment, and the results were really bad. And they spent this huge, and they weren't correct, right? And they spent this huge amount of time checking their code, and then checking the compiler. And then eventually they came to the conclusion that it must be the processor. And, you know, Intel thought they were nuts. Of course, there's no problem with a processor, like whatever, right? And then eventually they just took the simple case and did like all the division cases, right? And then compared them to the actual results and found the FDiv bug. And Intel basically had to replace every Pentium they sold. Classic stories. You can look it up on the web. Any other questions? Hang on. Yes?
Can we at least guarantee that floating point addition is associative between two floating point numbers?
The floating point division is associative between two floating point numbers. So I can flip the left and right in isolation, it will be the same. Yes. Yes? Why not use a second sign bit instead of a bias? The reason we use the bias instead of the second sign bit is because it makes the number line smooth. Otherwise, the number line would break. You'd have this weird discontinuity where you couldn't look at the number line and transition smoothly from one to the next. Does that make sense? And the reason this works is because we fixed the bias in one case, right, to match the bias of the other. So the fixed bias equals the bias of the end of the normalized range. Does that make sense? Okay. Any other questions? Have a great day, everybody.